Your teacher today is Dr. Bbosa Science. Today, 19th June 2019, we are going to consider electrochemical cells. This explains the chemistry of rechargeable cells, like that one in your phone. Terminologies, we start with electrode potential. We say that when a metal rod is dipped in a solution of its metal ions, it ionizes. The metal ionizes into metal plus an electron. For example, zinc will form zinc 2 plus 2 electrons. The electrons remain on the surface of the metal, whereas the positive ion will go into solution. So the electron remains on the surface of the metal, the cations will go into the solution. This creates a force of attraction between the negatively charged metal rod and the positively charged solution. Or this creates a potential difference between a negatively charged metal rod and a positively charged solution. This potential difference is called electrode potential. By definition, electrode potential is a potential difference that is set between a metal and its solution containing metal ions. Factors affecting the magnitude of electrode potential. 1. Temperature. The higher the temperature, the higher the electrode potential, because high temperature promotes ionization by supplying ionization energy. 2. Concentration of metal ions in the solution lowers electrode potential because it supplies ionization. Ionization equation is a reversible equation, so increase in the concentration of metal ions will drive the equilibrium to the left, reducing the number of electrons that remains on the metal surface. Then 3. Pressure. Standard electrode potential. This is the potential difference set up between a metal rod and a molar solution of metal ions at 298 K and 1 atmosphere. When the concentration is 1 mole, the temperature is 298 K, then the pressure is 1 atmosphere. The electrode potential is now standard electrode potential. When the concentration of metal ions is 1 molar, the temperature is 298 K and the pressure is 1 atmosphere. The electrode potential now is standard electrode potential. Factors affecting standard electrode potential. Standard electrode potential is an arbitrary measure of the ease of formation of hydrated metal ions from the metal. It involves free energy terms. From metal solid to metal gas is enthalpy of atomization. Metal gas to metal plus enthalpy of ionization. Metal ion gas, metal ion aqueous is enthalpy of hydration. So standard enthalpy change is the sum of atomization plus ionization energy plus hydration energy. Atomization and ionization are enzymatic reaction. So the higher the atomization or the higher the ionization energy, the more positive the standard electrode potential. Hydration is an exothermic reaction. Therefore, the higher the hydration energy, the more negative the standard electrode potential. Hydration is an exothermic reaction. Therefore, the higher the hydration energy, the more negative the standard electrode potential. Shorthand notation of half cell. We are saying that a metal dipped in a solution of metal ions constitutes a half cell, and the accepted form of writing half cell is to write oxidized form stroke reduced form. In this case, when you have zinc dipped in a solution of zinc ions, instead of doing this diagram, we write zinc 2 plus stroke zinc. Similarly, a copper electrode will be written as copper 2 plus stroke copper. Standard hydrogen electrode consists of hydrogen gas bubbled over platinized foil dipped in a solution that is 1 molar with respect to hydrogen ions at 298 K and 1 atmosphere. The standard hydrogen electrode was given a standard electrode potential value of 0 volts, and from now on is going to be our reference electrode. We are going to compare all other electrodes to standard hydrogen electrode. Measurement of standard electrode potential of a metal. The standard metal electrode is combined with standard hydrogen electrode as shown below. The two cells are connected to a 3 voltmeter, and the two solutions are connected by a salt bridge to complete the circuit. Since the standard hydrogen electrode is 0, the voltmeter measures standard electrode potential of a metal. For this reason, it is not possible to measure the standard electrode potential of a metal absolutely. It is measured relative to hydrogen electrode. Examples of standard electrode potentials of common metal electrodes are zinc is negative 0.76, copper is positive 0.34, silver is 0.80 volts. You don't have to cram these values because they will always be given in exams.
The Science Foundation College enamave ku Lwejjinja ng'oyingira kilomita emu. Somero lya Dene Boarding eri abawala n'abalenzi. Ku O-level tusomesa arts ne sciences, ate A-level tusomesa sciences zokka. Omwana mulete ku The Science Foundation College. Ffe tusinga okusomesa sciences. Okumanya ebisingawo kuba ku 0753 8 27 09. The Science Foundation College, based on sciences and based for sciences.
Electrochemical cell. This is a type of a cell in which a chemical reaction produces electric current. It is constructed by combining two metal electrodes, for example zinc and copper electrodes. Note that the metal electrode of most reactive metal is put on the left. And in this case, zinc is more reactive than copper, so it's going to be put on the left. And the left side constitutes the anode, the right side constitutes the cathode. Direction of electrons and direction of current move in opposite direction. Electron move from anode to cathode through the voltmeter. Current move from the cathode to the anode. The salt bridge completes the circuit. The anode oxidizes. Oxidation occurs at the anode to get zinc ions. At the cathode, copper ions get reduced to form copper. So the anodic reaction is oxidation, cathodic reaction is reduction. Overall reaction, by combining the two half equation is zinc minus 2 electron, you get zinc plus, copper 2 plus 2 electron, you get copper. When you add these two equations, you get zinc, the electron will cancel, plus copper 2 plus, aqueous will give you copper, solid plus zinc 2 plus. Given that the electrode potential of zinc is negative 0.76 V, the electrode potential of copper electrode is positive 0.34. We can develop electrode potential of a cell by adding. When we reverse this order, we reverse the sign of electrode potential. So zinc plus 2 electron, you get zinc. Here it is zinc minus 2 electron, you get zinc. So the electrode potential is 0.76. Then copper plus 2 electron, you get 0.34. So copper plus 2 electron, you get copper. So the electrode potential is 0.34. To get the overall equation, you add the two equations. So you add the two EMF and you get 1.10 V. Therefore, the EMF of a cell, EMF of the cell is equal to 1.10 V. If you cannot use this first principle, then you can use this formula and say that E cell is equal to E right hand electrode minus E left hand electrode. In this case, it becomes 0.34 minus 0.76, which is equal to 0.34 plus 0.76, which is equal to 1.10 V. The implication of EMF of the cell, when EMF of the cell is positive, then the cell is feasible. Or spontaneous. So when the EMF of the cell is positive, it means that zinc can reduce copper ions, copper and zinc 2 ions. Negative EMF, negative cell potential means that the cell is not feasible. Gibbs free energy, it says that energy is equal to NFE. For the last example of copper, N are 2 electrons from copper to zinc, so N is 2. F is the Faraday's constant, which is 96500. Then E is the EMF 1.0. This one will give you joule. This is the amount of work the cell can do. Example 1. Construct a cell using lithium and magnesium electrode. Given that lithium electrode EMF is negative 3.04. Magnesium electrode, the EMF is negative 2.37. So what we do, the more reactive is put on the left. How do you know the more reactive? Write a number line. Negative 3.04 is on the left of negative 2.37. So it means that lithium is going to be the negative electrode. So the cell A, the cell is going to be lithium, is oxidized to lithium plus. Then we put a solid bridge Then magnesium ion is reduced to magnesium. When we are writing a cell notation, the electrode on the left is reversed. In this case, we have started with lithium, goes to lithium plus. The electrode on the right is written as it is. Magnesium goes to magnesium plus. Write the reaction at the anode. Anode is on the left. So at the anode B, anode there is oxidation. The electrode on the left is the anode, so lithium solid minus electrode, you get lithium plus aqueous. Then at the cathode reduction occurs, so magnesium 2 plus 2 electrons, you get magnesium solid. Then C, cell reaction by adding the half equation is we get a cell reaction. So on the left get lithium but multiply by 2 to get 2 electrons solid plus magnesium 2 plus aqueous will give you 2 lithium plus aqueous plus magnesium solid. Then capture the EMF. We say that E cell is equal to E right hand electrode minus E left hand electrode. In this case, negative 2.37 minus 3.04, which is equal to 7, 9 minus 3, 6.0 V. A cell consisting of copper and silver electrode is shown below. So what is solution in any 1 molar solution of silver ion is in a soluble solute. So it can be 1 molar silver nitrate solution, because silver nitrate is the one of the soluble salts of silver, but you can use any soluble silver solute solution. Write the cell notation. In this cell, copper is oxidized to copper 2. Then we put a salt bridge. Silver is reduced to silver. Write overall equation that copper solid plus 2 silver ion is aqueous will give you copper 2 plus aqueous plus 2 silver solid. What is made of salt bridge is either conch solution of potassium chloride or ammonium chloride. What's the purpose of a silver bridge? To complete the circuit. The circuit without mixing the solution is. Example 3. The electrode potentials of lead and magnesium are shown below. Write the conversion for the cell that can be formed. We say that the most negative is put on the left and is reversed, is written in oxidation form. So it will be magnesium stroke magnesium 2 plus aqueous solid. Then you put a solid bridge. The one written, the most positive is written on the right, so it will be lead. Lead 2 plus aqueous goes into lead solid. Then write the equation of the reaction at the anode. At the anode, oxidation occurs. The electrode on the left is the anode, so magnesium solid minus 2 electron will go to magnesium 2 plus aqueous at the cathode. The electrode on the right is the cathode, so this will be equal to lead 2 plus 2 electrons, you get lead solid. Write the overall cell reaction. It will be magnesium solid plus lead 2 plus aqueous, you get magnesium 2 plus aqueous plus lead solid. Calculate EMF of the cell. E cell is equal to E right hand electrode minus E left hand electrode, which will be equal to right hand electrode. This one will be negative 0.13 minus 2.40. So when you subtract this one from this one, we get 702 volts. What does the EMF imply? It is positive. It is positive, and therefore the cell is feasible.